Today, the Event Horizon Telescope has given us an update on their search to image the event horizon of Sagittarius A star, which is a supermassive black hole residing at the center of our Milky Way. So I thought I would review what we know about Sagittarius A star, what the Event Horizon Telescope is hoping to see, and how they are hoping to achieve it. So to start with, here are some facts about Sagittarius A star. The black hole is located at a distance of 26,000 light-years. In terms of a time delay, that means that at the time the photons from the event horizon left to head towards the Earth, humans had already invented fire, but they had not had the idea to domesticate animals yet. Pretty big time delay. In terms of cross-galaxy distance, and maybe more relatable units, if our sun is over here, we are about 8,000 parsecs from the center in one of these arms. Sagittarius A star has a mass of 4 million suns, with a quite sizable error of about 500,000. So these things are hard to measure. This size, in terms of an event horizon, and this mass, means that the object is so heavy that there is a large area around the actual object, which is in the center, the event horizon, from which even light cannot escape. And the size of this region for Sagittarius A star is about 17 suns across. We know that this object is a black hole from two sources of information. The first one is the orbits of stars located around the black hole, which is what I have here in this movie. So this is a time-lapse of the position of stars taken in the center of the galaxy. If you look at this blob here, you can see it's going in kind of a circle. Now, it's kind of blurry and hard to see because astronomy is hard, and if you have some of these blobs coming too close, you get all these weird aberrations due to atmospherical blurring, and it's all very difficult. But if you go frame by frame, and you look at where the stars are and where the center of each blob is at every frame, you're going to find that some go in circular orbits like this, some go into very tiny orbits like this, and some are further away. They're moving in orbits more like this. And that's exactly the same as what we see in our solar system, with the sun at the center and the Earth going round in a big circle. The only reason the Earth is not escaping is because the sun keeps pulling it in. And if the sun was slightly heavier, our orbit would also be different. It might change to a different type of ellipse, more like this. So by looking at how fast these stars are moving, what orbits they are following, knowing how an average star is, which is this brightness, we can work out how heavy the thing which is pulling them needs to be. And then we get this number. And the large error is because it's very hard to know where exactly these orbits are. So you've seen the movie, it's all very blurry. And it can depend on where exactly you put the center. This is the kind of range that is compatible with these very tight orbits followed by the stars. And then the second way we have of measuring the mass of Sagittarius A star is from what we call proper motions. This is a technique that we have used in other galaxies than our own too, because in galaxies other than the Milky Way, we don't actually see individual stars. They are way too small to see in galaxies outside the Milky Way. But we have applied this technique in those galaxies and in the Milky Way, and it gives the same answer. So for this technique, you observe many, many more stars than the ones for the orbit, but for a much shorter time. So you don't need a very long time frame for this. You just observe where they are and where they are currently going. It might be, this one might be going away, this one might be going towards. Then you do this for many, many more stars everywhere around the central region of the black hole. And if you put a very large mass in the center, such as a black hole, these motions will not be exactly random. They will have a preferred orientation. They will be on partial orbits, kind of distorted by the presence of this very heavy mass. And this overall statistical effect is what we are looking for. And to do this, we can use 1,000 stars or more. And it's not only the motions sideways that we need to see, because we cannot see these tiny motions in galaxies other than our own. But we can also do this with the 3D motions, so to see if they are going towards us out of the paper or towards the paper, because these orbits are not only 2D, they're going out of the paper and back in. And by looking at the total orientation of all of these guys in a statistical sense, if they have a preferred direction or not, we can deduce how much mass has to be added in order to deform all these orbits in this way. And we get exactly the same answer, well, in this range, as we do with using only the orbits which are really close. So we are reasonably confident that it's roughly this big. Another interesting fact about Sagittarius A star is that it was not first identified as a black hole. Actually, many years ago, when we first pointed radio telescopes at the sky, we identified a very bright radio source right in the center, where we thought the center of the galaxy should be. This center, by the way, which is very close to the equator. You can usually not see it from Europe. It is a bit too far south. You have to go to Chile or Southern California to be able to see the location of Sagittarius A star on the sky. But anyway, how can we see something coming from a black hole? How is that possible? After all, black holes are so heavy that not even light can escape from their event horizon. So how come there was a bright radio source at that location? That's going to be a very big question. And to start answering it, we have to go back to our Earth going around the sun. So the Earth goes round and round the sun. It has gone around and around the sun for millions of times, always roughly on the same orbit, very, very small variations. And the reason that it hasn't stopped spinning and is still going is that in space there is no friction. So you might remember from your physics classes that if you make an object move, it will not stop unless something actually makes it stop. So, for example, if you have a poorly drawn football and you're kicking it around the ground, it should keep moving forever. The only reason it doesn't is because the floor isn't smooth. And you can see this because if you kick it on different surfaces, it will go more or less far. So at the very small scales, the floor is taking a bit of energy from the ball as it rolls, and that's why it stops. But in space, there is no friction. So the planet can keep moving and moving around the sun because it's not colliding with these tiny, tiny things. There's not enough stuff in the way to slow it down. Now, it's a bit different if you're around the black hole. So I'm going to draw some scales here. If this is a Sagittarius A star, it has an event horizon of about, we said, 17 suns. There is a no-man's zone of about 50 suns around it, where matter can never escape. So the event horizon is where light cannot escape, and this, what we call the Cisco, is the area from which matter can never escape. So if you try to spin in this, no matter how empty space is, no matter how fast you are going, you're always going to spiral in. And that's because a black hole only behaves like a star on very large scales. So the typical scales of the region around the black hole from which it's feeding, what we call the accretion disk, is about 500 suns. And at the edge of this region, the shape of the gravitational bending of space-time by the black hole is very much like a normal sun, like any mass, really. And as we go more towards the center, you start needing more and more general relativity to explain the motion of things until you get to this area in which it doesn't behave like circles or ellipses at all. But even on these larger scales, when the motions of particles are quite familiar because they resemble the orbits that planets have around stars, it tends to be a lot denser. So it's not empty to the same level as our solar system is. If a particle is captured into this region, it starts spinning. And many, many particles start getting captured because the black hole, being many millions of times heavier than the sun, has a larger area of capture. And all these particles sort of staying here in the middle of the galaxy where there's a lot of stuff floating around. All of this stuff starts getting captured on a very large scale. And because there is so much stuff, if you're a particle here, you are going to lose some of your forward momentum to the collision with all these other things around you. So you are going to start circular, but then you might spiral in just a bit. And every time you go around, you might get closer in just by colliding with these things. So the orbits are not nice and closed, like we are used to. And then the closer you get to the center, the worse it gets, because you would spiral, you would fall in anyway if you get too close. But the parts of the accretion disk which are emitting the most light are the ones from which the black hole is directly feeding, the very inner edge where the black hole is gathering things to spiral into the middle. And to understand which parts are shining and why, we're going to have to do some hydrodynamics. And hydrodynamics is a famously very difficult subject. As I'm sure most of you have seen, these simulations when we just throw air at like an airplane wing, which is quite a simple thing really. And you can see that the air immediately has this complicated behavior with turbulence and eddies, and it's going all over the place. And this is only air, right? We're throwing all the air we can as something which is just a wing. A wing is a lot simpler than a black hole. In air, you do have some things to worry about, like the density of air, where it gets compressed at the front. You have a pressure, of course. And you might even need to worry about temperature if you're dealing with something like an airplane jet. But for a black hole, it's a lot harder, because in addition to these things that the air can do, what we're doing is really throwing as much gas as possible at an object which is already extremely complicated. So you have all these additional problems, for example, self-gravity. So air doesn't self-gravitate. If you have a bunch of air, it's not going to suddenly be attracted to itself and break into lots of little clumps spontaneously. So that's not great. We have all the problems of plasma physics, because the air is so heated that it starts exchanging electrons between one part of the air and another. It starts glowing, it starts absorbing. You have to worry about what it's made of and how all the electrons are flying around. And you have the fun topic of magnetic fields, which make everything extremely complicated, and many more effects which are in addition to what is already an extremely complicated problem. So this is one of the hardest parts of astrophysics, in my opinion. We have a few models how we think the accretion disk around the central area of a black hole behaves. But really, all that we really see is different parts of it emitting different types of light, and we have to ask ourselves with simulations and models, what would happen if you throw a lot of gas at a black hole? Where would it go? What would it do? And that's very hard. But anyway, so if this is a black hole and it's absorbing stuff from all directions, so like a galaxy, a black hole, the gas falling into a black hole will come in with some angular momentum. And it has no way of losing that. It has a preferential direction of spinning, especially if it's dense and these things are colliding with each other all the time. All the things that are falling in will settle into some sort of disk on a very large scale, because it has to, just like in a galaxy it does. So what we think is happening, that very far away from the black hole, you get this torus, this thick torus of gas. This is going all the way around, right? I'm just drawing it as a cut. And then as matter keeps colliding with itself, it gets thinner into what we call a thin disk surrounding the black hole, kind of like this. And the reason it thins out is because of instability. As you get closer, the plasma effects and the magnetic fields and pressure effects as well will force it to thin. There's pressure effects that are squishing it on this intermediate distance, especially if you're throwing lots and lots of material at it. It will become super thin. So that's if it's secreting a lot of gas from everywhere. Then there is a theory that if it feeds a bit less, then you will start building up a bulge in the center. So once it gets to the center, these effects of suppression and thinning will not be quite as strong. And then in this case, this stuff which is piling up will create kind of a funnel, and through that funnel you can get plasma particles ejecting into jets, kind of like this. If there are magnetic fields, they might coil around, and they might grab some of the particles on the side and also accelerate them. And finally, just because you have a thin disk, the part in this region, this matter here, which is in the process of spiraling in and colliding with each other very, very slowly, actually gets extremely heated. There's a lot of collisions happening, it's extremely hot, and there is some sort of what we call a disk wind, which is also pushing things this way, so roughly speaking. And in terms of what kind of light come from these different parts, you can have, for example, in this torus, which is far away, because of all this very energetic events happening in the center, you might get infrared light coming from the torus all around. These parts, which are very highly collisional, very hot, lots of pressure and compression happening, will produce very broad lines. That is to say, that they look very strange. Actually, black holes like this are the only place we see these features, because they really require a lot of very, very hot, agitated gas to happen. Then the actual jet, if you look face on, you might see some gamma rays and some X-rays, which are these plasma particles being accelerated just from the edge like this, and being sort of channeled. And if you have any clouds of gas still hovering around, maybe in the process of falling into this black hole, and they get collided with by this jet, these guys are the ones that we think emit radio waves. Of course, to work all these things out, you have to do simulations like the ones we do for jet planes, except with a lot more complications. And it's extremely hard. But we get all these different types of markers for where all these different things could be. And we have tested these models reasonably well on hundreds, even thousands, hundreds of thousands of other accreting black holes, not Sagittarius A star, but black holes which are in the process of feeding a lot, which we call quasars. And we have a lot of data of all these different types of light and what the ratio between different types of light is, how fast different parts vary, which give us all sorts of information. Sometimes we even get reflections, so we get like a flaring in a broad line on one side, and then a few days later we see it reflected on the other side because the light has gone like this. So we can even use that kind of information to try and map out these things. And this seems to be a pretty simple but reasonably solid picture. But we haven't actually seen this through telescopes yet, but we might. So what do we actually expect to see if the Event Horizon Telescope works and we can image this central part? What are some of the predictions that scientists have at the moment? Well, I have 3 examples in the recent literature that I found. One of them is a pretty vanilla model of an extremely hot and extremely thin disk around a rotating black hole. So what actually is there would be some sort of a disk like this, pretty thin. So high in electrons and extremely hot, and the black hole is also rotating. I have some images of that over here, right? And what we would actually see if this was the case, if it's actually some sort of crescent, so we would see this part sort of bent like this, like we can see in these images over here, which are different types of alignment, if you see it from face on, if you see it from the edge, and the kind of bending that you get. So immediately you notice that what we actually see is very deformed compared to what I have in pink here, which is what we think is actually there. By the way, these are fake colors, so red means there's more brightness. It's not just actually red. It's the scale here at the bottom. This is a model by Monika Moshi-Bratska from 2009. A slightly more complicated model that other people have predicted is that you could have a pile-up of gas in the center, which is channeling these jets that I talked about previously, and then an addition of jets over here and over here. And in this case, what you would see is also some sort of crescent shape, except now it will have a peak in the middle, sort of like an E. It will be very lots of tiny, tiny structure. So it's over here. This is a paper by Heino Falke from the Netherlands in 2013. And again, this is the different viewing angles. You can see this extra feature here, which is basically the jetting. And the black hole is again rotating, but in addition to the previous model, they also have a strong magnetic field in it, which is channeling this jet. And the last model which people have managed to simulate what the observations would look like is a slightly older model by Avery Broderick from Harvard, which in the accretion disk, he proposes there might be a particularly bright spot somewhere, maybe a cloud that's not completely disintegrated or for whatever reason. And then what you would see is some sort of bending of the light like this, and a multiple image like on the actual black hole, like right on the edge where the black hole disk is. So it's these models. So you can see there's two components, one there and a second one there. And here too, it has this very asymmetric multiple components shape, depending on what angle you look at it from. So in this case, it's a hotspot model. Right, so all of these, what we would actually see, these plodgers, are very different from the models that are actually underneath. And the reason they are so distorted is because of some particularly nasty consequences of general relativity. In my last video, I talked a bit about the effects of gravitational lensing and how they make us see stars in the wrong position on the sky during false solar eclipses. So if this blue thing is a star, and then you look at the same patch of sky later when a false solar eclipse is happening, so the sun is here but is covered by the moon, you will see that the star appears to be in the wrong place. But that's not all that gravitational lensing does. It's actually a lot worse than you think, especially when you're dealing with something that's 1,000,000 times bigger than the sun. So let's think about what's actually happening here. So here's a star, and here's us. Usually, the rays of light that would reach us would follow this nice straight line. But now, if the sun is in the way, it is bending these rays. So this ray, which would usually hit us, now it misses. And instead, the ones that hit us are the ones that left in this direction, and they got curved by the sun, and they hit us from that angle. So then we might think to ourselves, great, the rays are coming from this angle, so I guess the star is over here, right? Because that's where it should be. And that's why we see the rays coming from a different place in the sky. That's why the position has changed. But let's think about this star for a second. Let's make this a bit bigger. Because this star, if we are here, usually the rays that would hit us are the ones coming from half of the star, the half of the star which is facing us. Kind of this half of the star, from which these are angled towards us, like this. So we see one half of the star, just like we see one half of the sun. It's facing us. But because of gravitational lensing, when the sun is here, the light which makes this half of the sun misses us. We don't see this half anymore. Instead, the rays that reach us are the ones that went slightly up and then went down again. So the side of the star that we see is actually different slightly. It's more like this area, which is crazy because there is this part of the star over here which we would not see normally, and now the sun has come in and it's bent it so that it's now visible, even though usually it would miss the Earth by a whole bunch. So not only is the star in the wrong place, it's also been rotated compared to us. And that's only with the sun. If you're dealing with a black hole, this effect is magnified about 1,000,000-fold. So if you have a black hole over here, if you have a nice accretion disk and say some jets coming in like this, is a terrible drawing, and we are here. Now we might not even see the correct side of the accretion disk because the phase that's facing us this way, these photons will not reach us. They might actually be deflected and go a completely different way because the bending is so ridiculously strong. But the rays from the other side, which go this way, might. So if this happens, we would see the far side of the accretion disk on the wrong side of the black hole. So if there's a bright spot here, we would actually see a mirror image on the other side too. And maybe if some rays are here, we would see it here too. So now this spot is appearing in many different places. And all clouds that are being hit by this jet on the back, the same thing is happening. They're being bent in a completely different place. They show up in the completely wrong spot of the image. And that's why we saw all these complicated features and all this weird bending happening in all these models. Even though this is just an accretion disk and a jet, but all the light which is being emitted, ends up in the completely wrong place because it's so ridiculously distorted. And it's hard to get a feeling for this by just looking at these. You really have to run full simulations and think about where each ray of light is going. So as you get closer to the event horizon, these photons will never escape. But if you just graze it, you can actually go around a few times and then escape. That is how strong the gravity is. If the photon misses by only about an inch, it might coil 5 or 6 times before escaping. I mean, it will just, all the light from these structures to our eyes will look completely messed up. Now, interferometry is a clever trick, but it doesn't really produce images in the same way as we might be used to. This is the same, this time I'm only showing 2. So say the light is coming in at this angle, and you have a time difference. This one is being hit slightly later. So what interferometry does not give you is an astronomical picture in the common sense of the term. So you're not going to get a picture like this, with a value of photons at each pixel. Say this is your event horizon, it looks kind of like this. This doesn't give you a value of how many photons come from each part on the sky. This is not what is being measured with interferometry. It doesn't scan space for photons, it scans space for time delays. Now this gets very mathsy. I don't want to give a lot of maths. We will be here forever. So I'm going to use an analogy. It's a bit like a Fourier transform. So a Fourier transform is something that's useful for storing sound. And we'll see why this is useful in a second. So as you probably know, sound is a variation of the pressure of the air with time. So when the pressure of the air changes with time, it goes whoop, at a particular oscillating speed, that produces a sound. And the Fourier transform is simply containing the same information, but in a different kind of representation. Instead of storing it with time, we will just analyze this for what frequencies are present. So in this case, this frequency, which is quite fast, is present a lot. So in frequency space, this point will be represented. It's particularly powerful where there are no other frequencies. And if you make a more complicated sound, for example, if you add a slow varying sound over it, then you might get a different peak here. If you get lots of small details, lots of more complicated sound signal, then your Fourier transformed sound will also be complicated. But mathematically, these two representations contain exactly the same information. It might not be stored as a signal with time, but it can always be reconstructed from the Fourier transform and the other way around. You can always turn one into the other. If you know one, you can know the other. And that's exactly what interferometry is doing, but with space instead of time and frequency. So for example, if a source on the sky is a simple blob, what an interferometer would be measuring is what spatial wavelengths of light are present in this image. It's encoded as a different system of units, which is a bit like frequency. So in this particular example, a blob stays a blob, which is of a different size. But if you have something a bit more complicated, or even just as simple as 2 blobs, then your Fourier transform spatial representation is going to look very, very different. Actually, it's going to be like a series of fringes, kind of like this. It's not obvious why the time delay produced by something like this will translate to a wavelength space that looks like this. You really need to do the maths for that. So you can take my word that these translate into each other. The point being that with time delays, what we are really measuring is this one first. And then we can transform it using an inverse Fourier transform back to what it would be in real space. And the ALMA telescope has done this very successfully, hundreds of times, so it's completely feasible. But ALMA has hundreds of antennae. And the Event Horizon telescope, even though it's the size of half the Earth, at the moment only has 4 sites. So what is the status of this experiment, and what have they found so far? This was the subject of the latest paper, which came out this week. in which they compare 3 models with the observations they already have. So these 3 models are one with multiple images of where the black hole event horizon would be. So that is this model with multiple images. They have a model in which what they're looking at is actually just a star, just to make sure it's ruled out. And they have a crescent model, which is kind of like this, representing the most likely models, which are these, which are just a thin disk model, quite simple. And in the paper, they transform these into the Fourier space of what the time delays actually look like. So we can see this here. The two models I have on the left and on the right are the 2 models that they are transforming. So the left model would look like a blob surrounded by fainter lines, like this. While this model of a crescent would look like a bright blob in the center, surrounded by a dark, very dark ring, and then a thinner ring around it, like this. These are the 2 things you can see here in the bottom, if you look closely. And this one, as we mentioned before, if something is a sphere on the sky, it will stay a sphere of a different size in Fourier space. And now, thanks to the addition of the telescope in Chile, which is all new, this is the first time we see data from the telescope be added to this, they have covered a larger part of this space. So with a telescope like ALMA, you can cover all of this, all the relevant wavelengths that you need to reconstruct the real space image in 1 or 2 nights. But because they only have 4 antennae, it's taken them a lot longer. So currently, they have explored sort of this part of it, and this part of it, and like some of these parts over here, and maybe the center a bit, which are these gray spots in these images. These gray spots are where they have actually measured the Fourier space. So it's not a very large coverage fraction of the total space. And that means that they don't have a visible image yet, because they don't have enough information in this space to be able to reconstruct what we would actually see. It's a bit like if you were trying to listen to a music file and you're downloading a compressed version and you only have like 20% of the compressed version. Even if you have 20% of the compressed version, doesn't mean you have 20% of the song, or even the song at 20% quality. Compression just doesn't work like that. And Fourier transforming is very similar. So we have a bit of the compressed Fourier transformed version. Once this is full, we will be able to invert it into the real image. But even with this tiny coverage, by comparing what they see in these bits with these predictions, which are the transformation of these, they can already say that this model is kind of okay. It kind of agrees with observations, and this one does too, but this one does not. So they are definitely ruling out that the thing they are seeing is just the thing that is there is just a bright blob. So if we have the summary of the status of the Event Horizon Telescope, they have finally added the baseline in Chile. Now, with the addition of this 3rd point in Chile, once this is complete, the resolution they can have by going back into real space will be about 3 times the Schwarzschild radius of the black hole. And the Schwarzschild radius is the area that's from which light cannot escape. So if the resolution is 3 times this, it means that their pixel size will be about this big, which is not too bad. You know, it's probably enough to see what shape it will be, and hopefully one dark pixel in the center. But hey, finally, with the addition of Chile, they are getting down to this resolution at which we will finally see the event horizon. They have checked that there is something there where Sagittarius A star should be. They have checked that the brightness is correct. It agrees with both the models, all the models which say how bright an accretion disk should be. The size of the object, they can constrain already from some of this partial information that they have, and it's fine. And they even know that the object has to be asymmetric, so it's not just circular. And so they can rule out this model. There is something not symmetric about it, whether it's multiple blobs or whether it's a crescent. It is definitely not round. So that's good. You know, they're on the way. So when can we expect to finally see the picture of the event horizon surrounding Sagittarius A star? Well, the ETA is soon. So in 2017, the Event Horizon Telescope added the ALMA array, the most successful interferometer ever, to their baseline. It's also located in Chile, but it's a lot better than APEX. And so with the addition of ALMA, they can definitely break the resolution that they would need to resolve the Schwarzschild radius. It's a big improvement in quality. And they have already observed with it. They already observed for it for many hours in 2017. And they are probably analyzing that data as we speak. Someone in that team might be currently seeing the first image of a supermassive black hole event horizon, which I think is pretty cool. And I hope they process the data and release the image soon. I think everyone will be extremely excited. All right, so this is it for today. I hope this was interesting and you understand a bit more about how the Event Horizon Telescope is supposed to work. And I will see you next time. Bye.